Hello everyone, I'm Yuanda Wang, a PhD student from Michigan State University. I'm glad to share our work, GhostTalk, interactive attack on smartphone voice system through power line. This work is done with my lab mate Hanqing Guo and my advisor Dr. Qiben Yan. Usually, we use voice assistants to remotely operate our smartphones. For example, make a phone call or send a message. At the same time, our smartphone knows our privacy as well. For example, our address and contact phone numbers are saved in our smartphone, and your smartphone also knows your current location, and all this privacy can be answered by your voice assistant. There are many existing attacks targeting voice assistants. However, these attacks are facing challenges. The first challenge is that such inaudible voice commands are easy to fail when launched in noisy environments. Also, these attacks require prior knowledge about the authenticated user's voice, but sometimes it's not realistic in real world. Then, the attackers cannot compromise voice assistants. Third, it is challenging to query privacy information via inaudible voice commands. If the response is audible, the victim users will be aware of the attack. If the attackers mute the phone, then the response cannot be obtained by the attackers. Here comes the first question: how do we address these challenges? In this work, we explore the feasibility of launching inaudible voice command attack by other medium besides over-the-air. We noticed that smartphone manufacturers, including Apple and Samsung, they have removed 3.5mm headphone jack on their new products, which means that we must plug our headphone into the charging ports. The right figures display the circuits of Lightning and USB charging ports. We can find that they do not only charge smartphone, but also enable audio signal transmission. Therefore, it is possible to inject and eavesdrop audio signals through the charging ports. Furthermore, we find out commercial adapters are designed for using headphone while charging. Different from standard charging cables, the microchip in the adapters enable audio transmission. Next, we disassemble the adapter. We see that there are audio cables, including microphone, ground and speaker, and charging cables. If some attacker can replace the standard charging cables with this malicious adapter cable, they can launch a new inaudible voice command attack by manipulating or monitoring the electric signals on the microphone or speaker. We want to test the feasibility of this new attack. First, we modulate an audio "Hey Siri" as an electric signal and inject the signal through the microphone cable. Then, we get an audio input from the smartphone. We can see the audio input waveform match the electric signal. Conversely, we use the smartphone to play a spoken word, password, and we monitor the voltage difference on the speaker cable. We also find that the voltage waveform is same as the audio waveform. In this way, we prove the feasibility of this new attack. Also, we noticed that it is practical to replace the charging cable in the shared power banks and launch the attack. The attacker only needs to rent and modify the power bank. The next user will become the victim of this new attack. We named this new attack GhostTalk since it's inaudible and interactive. Here is an example of GhostTalk attack. In a shopping mall, the user ran out of the smartphone battery and he uses a shared power bank to charge the smartphone. Unfortunately, this power bank is malicious. The attacker can remotely inject and eavesdrop audio signal and hack the smartphone voice system. For example, he can ask the user's home address and ask the voice assistant to open the door. We give the GhostTalk attack system design. As we discussed in previous slides, there are three main challenges for existing inaudible voice commands. The first one is the robustness in noisy environments. For GhostTalk attack, the signal is transmitted over the cable. Therefore, outside noise has no impact on the electric signal, and the attack can maintain high performance in noisy environments. Second, to achieve interactivity, we add two resistance to emulate the presence of a headphone. When the smartphone detects this fake headphone, it will not play audio through its loudspeakers. Then, the attacker can inject modulated audio signal to the microphone cable and eavesdrop audio signal from the speaker cable. Third, since sometimes we don't know the user's voice and we need to bypass the voice recognition system, fortunately, we notice that when we keep pressing the button on the headphone, it will activate the voice assistant without authenticated voice. Inspired by this idea, we add a MOSFET between the microphone and ground to simulate a fake press button, and the attacker can remotely control the MOSFET to awake the voice assistant without the user's voice. More details can be found in our paper. As a result, GhostTalk has many new attack scenarios. First, the attacker can ask the voice assistant about the user's privacy, like name and contact information. Second, once the attacker obtains this privacy information, he can launch Ghost phone call. In the phone call, he can even talk with the victim's contact. Third, GhostTalk can hack the verification code. Once the attacker knows the user's phone number, he can log in the account through the phone number. Then, the server will give a phone call to send the verification code, and this code can be eavesdropped by the attacker. However, sometimes the users do not use shared power bank. Here comes another question. What if an attacker cannot modify the charging cable? Can we launch attack through standard cables? For example, in hotels and airports, the users charge their smartphones through public USB charging port. Is it possible to launch any attack through these USB ports? In our experiment, we found that when the smartphone battery is already charged to a high level, the charging current shows patterns related to the audio signal played by smartphone loudspeakers. To validate the cause of said channel, we did a simple experiment. We used an iPhone 10 with two speakers and respectively play a chirp signal through the bottom speaker and top speaker. Then we stop playing and shut off the smartphone. From the spectrogram, we can see that for bottom speaker and top speaker, the leaked audio signals have the same strength. Then, when we stop playing, the audio signal pattern disappears, but the noise is still there because other firmware is also consuming the charging power. Finally, when we turn off the smartphone, the noise disappears as well, which means that this phenomenon is definitely caused by power consumption said channel. We introduce GhostTalk SC attack, where SC stands for standard cable. Different from GhostTalk attack, GhostTalk SC can eavesdrop audio signal while users are charging with standard charging cables. The attackers can hide a small chip in the USB charging port and analyze the current signal. Since the extracted audio signal is too noisy, human ears cannot recognize the speech content. To address this issue, we use a CNN model to recognize some sensitive information in the speech, for example, spoken digits, to hide password, SSN number, or verification code. We use STFT to get spectrogram image and denoise it, and it will work as the CNN input. Our network is inspired by AlexNet architecture and trained with public spoken digit dataset. Finally, the model will output the prediction of spoken digits. Next, we will evaluate our attack. Our attack hardware are small-sized devices and all of them are cheap. The total cost is less than $20. We launched our attack on 9 different smartphones. GhostTalk can achieve both injection and eavesdropping on all victim smartphones without any prior knowledge about the user's voice. For all these victim smartphones, the attack success rate are 100%, since our attack directly inject electric signals into the smartphone. Next, we do a user study to test whether human ears can distinguish injected speech during ghost phone call attack. We recruit 20 listeners, and each of them will listen to the natural speech and the injected speech samples with same content. Then they need to select whether these samples can be distinguished or not. If they are distinguishable, they should pick the likely injected speech. From the result, we can see only 15% of answers are correct. We also test GhostTalk robustness for liveness detection models. When dealing with replay attack samples, these models all maintain low error rate. However, for GhostTalk attack, they fail to detect injected signals, since the audio is not played with a loudspeaker. Moreover, we can adjust the GhostTalk injection frequency to better spoof these models. Then, we evaluate the robustness in noisy environments. We compare the injection attack with replay attack. In noisy environments, replay attack failed to work, but GhostTalk can still keep high attack success rate. Similarly, in noisy environments, audio signals from GhostTalk eavesdropping are still clear as well. Next, we evaluate GhostTalk SC attack performance. We launch the attack on the same smartphones as GhostTalk. For most of smartphones, the recognition accuracy is high. The only exception is Poco phone. One possible reason is that its power consumption from other firmware is too high, and we cannot extract clear audio signal from it. Also, we test GhostTalk attack SC performance under different volume settings. The first figure shows the spectrogram of original spoken word 1, and the second figure is what we recovered from the charging current from the highest volume level 16, which is very close to the original one. But if we turn down the volume to level 12, the quality will degrade. For lower volume level like level 8, only a few patterns remained. For 3 different models of smartphones, we find that loudspeaker volume and classification accuracy are positively correlated. Finally, we test GhostTalk SC robustness in noisy environments. Similarly, since the noise cannot disturb the power consumption set channel, our GhostTalk SC attack maintains high accuracy even in extremely noisy environments. Here, we'll give some countermeasures. For GhostTalk, users can disable the voice assistant activation by headphone to defend this attack. Or some phones will give a notification when it connects a headphone, and it will help the user to detect GhostTalk attack. For GhostTalk SC attack, users can stop charging after reaching high battery level to protect your privacy. Also, as a discussion, we find that when users are touching the screen, the GhostTalk SC performance may degrade since screen touching will cause more power consumption, but we can still recognize patterns between each screen touching. Here is the conclusion. First, GhostTalk is the first interactive and inaudible voice command attack towards smartphone voice assistance over the charging cables. Second, we also propose GhostTalk SC, an eavesdropping attack capturing audio signals from power set channel. Finally, we test GhostTalk and GhostTalk SC attacks on 9 different models of smartphones, and the evaluation results show that both attacks achieve high success rate and resilient to environmental noise. Thanks for listening, and I'm ready to answer questions.